back to the channel. It's Jake again, and today I have a video about functionals and basis sets and choosing the best ones for your DFT computational chemistry. This is something that I wish I knew more about when I started doing computational chemistry, because it can be quite useful in reducing your computational time and also improving your results. So this obviously isn't going to be a completely conclusive video. There's many details about functionals and basis sets that I could go into and probably go beyond my knowledge, but this should be a good starting point for determining what computational basis set and functionality you should use for your type of calculation. And if you want to learn further, I'll provide links and articles that you can read to get better information and more conclusive results. So the first thing I'm going to be talking about are functionals, which is actually how the calculations are computed. It's not the specific series of calculations that are run, it's how they're all combined together into the final result. The first thing I'll talk about is Perdew's Jacob's ladder. This was first described by John Perdew in this article written here at the bottom. And it's basically describing how, as you increase the complexity of your calculation, how things will change. So starting out with the Hartree-Fock, which is the most basic form of computation you can perform. And as you go up on the ladder, you add another level of complexity that increases your computation time, but also probably will increase the accuracy. Not necessarily that the higher you go on Perdew's ladder, the better results you'll get, because sometimes you're adding additional calculation pieces that will not improve the performance of your calculation. So you start here at Hartree-Fock, then you add dependence on the density, which goes to LDA type functionals. Then you add the gradient of the density, which moves to GGA type functionals. Then you add kinetic energy density, which moves to meta GGA type functionals. Then you add dependence on the occupied orbitals, which are hybrid GGA or hybrid meta GGA type functionals. And then finally you can add dependence on virtual orbitals, which moves you up to double hybrid type functionals. And ideally, this would continue until you get complete chemical accuracy, but this is where we are at currently. And based on the type of calculation you're performing, you'll want to choose one of these rungs on Jacob's ladder, such that you get enough chemical accuracy, but you're not increasing the computational cost too significantly. So looking at the various types of computations you could be performing, such as dimers, isomerization energy, thermochemical calculations, activation energy barrier heights, based on the type of calculation you're performing and what's most important for your calculation will determine what level of Jacob's ladder will be most useful for you to use. So as you can see, for non-covalent easy dimers, adding dispersion will greatly improve the accuracy of your calculation because you'll have the lowest root mean square deviations. Whereas for other types of calculations, such as isomerization energy of difficult computations, the dispersion energy will improve your calculation a little bit, but not as significantly as for other types of calculations. So if you look at these different graphs, you can see which type of calculation has the best rung on Jacob's ladder and where you would want to fit your calculation to those rungs. So based on the calculation you're performing, see which type of calculation fits most closely to your calculation and choose the rung that improves the accuracy without increasing the computational cost so significantly. Looking at specific functionals, this paper by Mardirossian and Head Gordon describes the root mean square deviations of the same types of calculations and includes equilibrium bond lengths and equilibrium binding energies. And you can see for various types of functionals how the different functional improves the accuracy of the calculation. So as you can see, B3-lip, which is probably one of the most common types of functionals used for computational calculations, doesn't have the greatest performance among many of these calculation types. For equilibrium bond lengths, it is quite accurate, so if you're purely looking to calculate the geometry of your species, this might be a good functional. But if you're doing one of these other types of calculations, you might want to move to a different functional. So something to consider for your functional is the use of dispersion correction. Dispersion correction adds a correction factor for dispersion and van der Waals forces that are in the system, and they're particularly useful for calculations that have long-range interactions. Dispersion correction does not greatly increase the computational cost, but in many cases can greatly improve the accuracy of your calculation. So in most cases, it's better to add dispersion correction to get the most accurate results because it will not increase your computational time. There are a few types of dispersion corrections: non-local correlation functionals, such as the VV10 functional, and these are built into the omega B97 series of functionals, such as omega B97X-V. There's also the empirical dispersion correction developed by Grimm, which is DFT D2, D3, D4, and then you can add an exchange dipole model to these Grimm dispersion corrections, such as Beck-Johnson damping. And to include these types of corrections, you want to add the extension to your functionals, such as B3-lip D-3BJ. So this would be B3-lip with Grimm's dispersion correction using Beck-Johnson damping. And if you want to look at various types of dispersion corrections, I put a link here at the bottom. So if you want to read more about those, you can go to this link and read more about it. As you can see, for non-covalent easy dimers and isomerization energy, by adding dispersion correction, the accuracy of the calculations is improved significantly. Even going from the more basic type of D2 type dispersion correction, you'll greatly improve the accuracy of the calculations. But something to take note is many functionals have dispersion correction already built in, so you need to determine whether your functional already has dispersion correction built in, because if you add dispersion correction to a functional which already has it, you will be correcting for dispersion twice, and thus decreasing the accuracy of your results. So something like omega B97X-V has dispersion correction already built in, so you would not want to add an additional dispersion correction. But something like B3-lip does not have dispersion correction, so you would want to add this to your functional. If you are debating what functional you should use for your calculation, I highly suggest reading this paper by Mardirossian and Head Gordon, published in 2017 in Molecular Physics. It goes into great detail about all the different types of functionals you could use, how they're calculated. It talks about Jacob's ladder, and it has a huge benchmarking data set for all the different functionals for various types of calculations. So if you're trying to find what functional would be best for you, I would look into this paper, decide which type of calculation corresponds to your calculation the best, and pick a functional that gives the lowest error. This paper doesn't talk so much about computational cost, so the best thing I would suggest is to pick a computational functional that has a very low error for your type of calculation, and see if you can perform it in a reasonable amount of time. And if you are not able to perform it in a reasonable amount of time, maybe move to a slightly less accurate functional, but you'll be able to determine which of those functionals have the most accuracy for your type of calculation. This paper was listed in the previous slide, and I also have a link to the DOI in the description, so yeah, I highly suggest looking at this paper. The next thing that I'm going to discuss are basis sets. Where the functional determines how the calculations are computed, the basis set determines what is actually being computed by the computational chemistry software. There are a number of different families of basis sets, such as the Dunning basis set, which includes CC-PBDZ, the Popel family of basis sets, which includes 631 plus G, the Karlsruhe family of basis sets, which includes DFT TZBBD, the Jensen family of basis sets, which includes PC1, PC2, the Los Alamos family of basis sets, such as Lanel 2DZ, and the Stuttgart family of basis sets, SDD. Each of these families of basis sets were developed by a different set of researchers and calculate your computation in a slightly different way. Another important thing to note about your basis set is the zeta value. What the zeta value is telling you is for each core or valence orbital, the number of functions being used to calculate that core or valence orbital. Increasing the zeta value will greatly increase your computational accuracy, but it will also greatly increase your computational cost. The minimal basis set calculates one function for each core or valence orbital. I would not suggest using a minimal basis because they are seen to be quite inaccurate. Double zeta basis sets will calculate two functions for each core or valence orbital. Some examples of these are PC1, DEF2 SVPD, 631G, and CC-PBDZ. You can see in the title of some of these functions that they have a D, which indicates to you that the basis set is double zeta. I would recommend at least a double zeta for any calculation you're performing because it will provide a much better accuracy than the minimal basis without being so computationally expensive that they cannot be performed. For single point energy calculations, I would highly suggest at least moving to triple zeta, which has three functions for each core or valence orbital. Some examples of these are PC2, DEF2 TZVP, 6311G, CC-PBTZ. These basis sets will be slightly more computationally expensive than the double zeta, but will greatly improve the results of your calculation, as I'll show in the next slide. There are even higher zeta values that you can use, such as quadruple and quintuple zeta value, and these will improve your calculations to a greater degree, but will also be highly computationally expensive. So unless you're calculating a small molecule and only a single point energy calculation, I would not suggest moving up to quadruple or higher zeta value calculations. In a paper published by Yueshi Mao in the Journal of Chemical Physics in 2016, he performed a benchmarking study for 148 neutral molecules and their atomization energies. In this paper, he showed that by increasing from double zeta to triple zeta calculations, the RMS error is greatly decreased. As you can see in these benchmarks, moving from triple zeta to quadruple zeta did improve the accuracy to some extent, but did not have nearly the same improvement as moving from double zeta to triple zeta. These results were consistent over a range of functionals. So based on these results, I would highly suggest, if you can, moving to a triple zeta basis set to greatly improve the accuracy of your results. One thing to note about your basis set is whether or not it includes polarization functions. Polarization functions allow for the polarization of the orbital angular momentum of each orbital you're calculating. So if you're calculating an electron in the p orbital, it will allow for the polarization of that electron to the d orbital. Polarization functions greatly improve the accuracy of your computation in most cases, however will slightly increase the computational cost. The Dunning, Karlsruhe, and Jensen family of basis sets include polarization functions by default. The Popel family of basis functions can be addended to include polarization functions by adding d for a single level of polarization or dp for two levels of polarization. One thing to note is that the Lanel 2DZ and SDD basis sets do not include polarization functions. So if you believe that your calculation will be improved by the addition of polarization functions, I would not suggest using these basis sets. In a paper published by Pitman et al. In the Journal of Physical Chemistry A in 2023, they performed a benchmarking of a range of calculations that include reaction energies, isomerization reactions, reaction barrier heights, intermolecular noncovalent reactions, and intramolecular noncovalent reactions. They found that the addition of polarization functions greatly improves the accuracy of the results. For the functionals MO62X, B3lip, and omega B97M-V, for all of the double zeta basis sets, they found that by adding polarization functions to the calculations, they greatly improved the accuracy of the results and reduced the mean absolute error. The same trend was seen for triple zeta basis sets, where adding the polarization functions greatly improved the accuracy. So I would suggest, if your reaction includes any of these types of effects, to include polarization functions into your calculation. Another thing to note for your basis set is whether or not it includes diffuse functions. Diffuse functions are useful for calculations that include non-covalent interactions. I would highly recommend adding diffuse functions for calculations of excited states, for anions, and for Rydberg states. For the Karlsruhe family of basis functions, you can add diffuse functions by addending the basis set with a D, such as with the DFT TZVP-D basis set. For the Popel family of basis sets, you can add diffuse functions by addending your calculation with a plus or 2+, such as in the case of 631 plus G or 631 plus G, where 1 or 2 diffuse functions are added, respectively. For the Dunning family of basis sets, you can add diffuse functions by prefixing your basis set with the AUG prefix, such as in the case of AUG, CC, PB, TZ. In this case, the AUG stands for augmented. One thing to note is that the LANL2DZ and SDD basis sets do not include diffuse functions, so if you need to have diffuse functions in your calculation, I would highly suggest not using these basis sets. Another thing to take into account for your calculation is whether or not to include an effective core potential. An effective core potential replaces the quantum calculation of the core electrons in heavy atoms with a pseudo or static potential. This means that the calculation will only perform the quantum calculation on the valence electrons. For metals and heavy atoms, the core or inner electrons will not greatly affect the computational results of your calculation. So, for these types of atoms, it's very effective to use an effective core potential because it will greatly decrease the computational cost without affecting the accuracy of your results. There are a number of different types of effective core potentials that I have listed here at the bottom of the slide. Note that these effective core potentials have an associated basis, meaning that if you use a specific basis, such as LANL2DZ, you would be best to use an effective core potential that matches this basis. The Karlsruhe family of basis functions, such as DFT TZVP, also has a family of effective core potentials, such as DFT ECP, and I would suggest using this family of effective core potentials if you're using this family of functions. In the link I've provided on the previous slide and also in the description of this video, you'll find a guide on QChem's website as to what each family of effective core potential classifies as a valence and core orbital. So if you look at the DFT ECP effective core potential, you can see that what it considers a core orbital are, for all of these atoms, is argon plus the 3d orbital, and for these atoms is the krypton plus 4d orbital, and then for these atoms is the krypton plus 4d plus 4f orbital. For other types of calculations, you can see at which section an orbital is considered core and valence. So if you'd like to learn more about the effective core potentials and the different models for these effective core potentials, look at this website to determine what exactly is considered a core or valence orbital. Another thing to note about computations is that you can have a split basis. So if you really want to use a specific basis for certain atoms, you can use it for those atoms and use a different basis for another atom where the basis is not available. This is something I did in some of the first calculations I performed, where I used CCPBDZ for all of the organic atoms such as carbon, hydrogen, oxygen, nitrogen, and sulfur, and then I used the LANL2DZ basis function for ruthenium because CCPBDZ was not available for this atom. This can be useful if you really want to use a specific basis function, and it's not available for all of the atoms in your molecule. In many cases, however, there are basis sets available for all of the atoms in your molecule, so really only use this if you want a specific basis that's not available for all of your atoms. The final thing that I want to show you is this website, Basis Set Exchange, which I have linked in the description. It's a very useful site because you can select all of the atoms that are used in your calculation. So let's say I was using ruthenium CNOSH. So if I wanted to use these atoms, I could go over and see that DEF2 TZVP is available for the atoms that I've selected. I could then go down and download the basis for whatever computational chemistry software I'm using. So let's say we're using QChem, I can get the basis set. And then all of the computational details will be available for me to use and input manually into my basis set. Another thing that is useful about this site is that for a specific basis, I can get all of the references that I would need for the use of this basis. So say I wanted to use the DEF2 TZVP basis, I can go here and select Get References, and it will give me all of the references that I would need to cite in my paper for the use of this basis. Note that you really should cite every paper that is used for the basis for all of the atoms you used, as well as the papers for the effective core potential, for the functional, and every other computational detail that you've used. With that, I'd like to thank you for your time watching this video. I hope it's been at least a little bit helpful in improving your understanding of functionals and basis sets, and I hope that it can provide a good starting point for understanding which computational methods you should use for your calculation. If you have any questions, feel free to leave them in the comments or send me an email, and I'd be happy to answer them to the best of my abilities. If you'd like to see another topic covered, feel free to also leave this in the comments, and I'll see what I can do about making a video about whatever topic you'd like to discuss. With that, thanks again for your time. Feel free to like or subscribe, and I'll see you next time.